gravity. Gravity. Now, gravity, in case you haven't heard of it before, is that little thing that keeps you on the ground and the planets orbiting around the sun, so it's actually pretty important. Now, Isaac Newton, and my guess is he was a dude that looked a little bit like this. He came up with the first reasoning of how gravity works. Now, he made a big long law, and I guess I might as well read it to you guys so people don't yell at me. His law goes something like this. Every object in the universe attracts every other object in the universe with a force proportional to the object's masses and inversely proportional to the square of the distance between their centers. You got that? Can you remember that? Well, I can't either. So hopefully, or excuse me, thankfully, he came up with a formula to represent the force or attraction of gravity between two objects. He says that the force or attraction of gravity is equal to the mass of object 1 multiplied by the mass of object 2, and I guess I probably don't need to do that, mass of object 2 all over the distance from their centers squared. Now, I want to emphasize centers because it's very important. Say you were trying to find the attraction or force of gravity between the Earth and the Sun. Now, typically, whenever you measure the distance between two things, you measure it like this, point A to point B. But whenever you're figuring out gravity, that's not the case. What you need to do is you need to figure out the distance between their centers. So the ruler would go from there to there if you had a ruler that big. So remember, that is how you calculate the distance from their centers. Moving on to the next topic, which is this. Basically, the weird thing Newton is saying is that gravity exists between any two objects with a mass. So he's pretty much saying that every object on Earth with a mass is attracted to you. Are you telling me that this meatball sitting in my room right now, it is attracted to me? Are you also telling me that my computer is like sucking into me right now, like me and the Earth? Are you also telling me, more importantly, and probably the most important thing of all, that the cute girl that was always in my science class and she's like, "Oh, Bucky, you're kind of weird," secretly and noticeably, she is attracted to me thanks to Newton's law? Well, even though she won't admit it, then yes, she is still attracted to you according to the law of physics. Now, the reason that you don't notice objects and you don't feel their attraction is because compared to the universe, you are almost nothing at all. You have such little mass that there is basically no attraction at all. Even though there is, got like a freaking cat hair in my mouth. Even though, oh, there it is. That's disgusting. Anyways, back on track. Even though there is indeed a small attraction between you and every other object, it's so unnoticeable whenever you compare it to you and the mass of the Earth. Why is that? Because, of course, whenever you're dealing with gravity, mass is a factor, and the bigger things have a stronger attraction. So that is why the mass of the objects is so important when calculating the force of gravity, but even more important is the distance between the two objects. And let me show you guys why that's the case. Whenever distance is quadrupled, for example, say you calculated something and it had a mass of 1, combined mass whenever you multiplied it, and also a distance of 1. We'll keep things simple. But that would mean that the gravity equals 1, and I know that these are, kind of fake numbers, but the gravity we'll say is equal to 1. Well, say we had the same two objects. However, now the distance is quadrupled, so this is 4. Well, what we need to do is the formula for gravity is distance squared, so when distance is quadrupled, the force of gravity would actually be 1/16 because 4 squared is 16. So that is how important gravity is, or excuse me, distance is when calculating gravity. Now, check this out. Say that I weigh 150 pounds. Now, I'm chilling here, right here, standing on Earth, so let's go ahead and figure out the force of gravity. Well, the center of the Earth, from the surface of the Earth, we'll say it's a nice even, let me draw my arrow, 4,000 miles. So right now, when I'm standing on the surface of the Earth, I weigh 150 pounds. Why? That's how hard gravity is pulling on me. Now, say over here, I'll draw another Earth. However, on this Earth, I am twice the distance away from the center. So instead of 4,000 miles, I am now 8,000 miles away from the center of the Earth. So, according to Newton's law, instead of weighing 150 pounds like I did right here, we say that, okay, my mass is the same, so we can keep that at a constant 1. However, my distance from the center has doubled. So we'll put that 2 squared. So I would now have an attraction of 1/4 as much as the original. So when I double my distance away from the center, I better label this, center of the Earth, I don't weigh 150 pounds like I did on the surface. I weigh 37.5 pounds. So that is basically the formula for gravity, and also that is why the masses of both the objects as well as the distance are extremely important. So you know how I said that acceleration due to gravity is 9.8 meters per second squared? Well, that's the case near the surface of the Earth. However, up here, when you get further away from the Earth, the acceleration or the force or pull of gravity on any object is smaller. So just remember that. The force or attraction of gravity on any object is going to be less and less, or in other words, weaker, the farther away you get from that object. So hopefully you understand a little bit more about gravity now, and we're going to be using these formulas to apply them to not only earthly objects, but objects such as planets, stars, all that good stuff. So